Somewhere in the Chilean Andes, on a mountain called Cerro Pachón, a camera the size of a small car just woke up. It's the largest digital camera ever built, and in its first few months of operation, it found something that hadn't existed in any catalogue, on any chart, in any database, anywhere on Earth, until now. 33 asteroids. All of them near-Earth objects. All of them brand new to science. That number probably sounds alarming. It's not supposed to. But before we explain why, let's sit with the question for a second. What does it actually mean when astronomers say they've found dozens of new asteroids near Earth? Does it mean they're coming for us? Does NASA have a plan? And why is a single observatory in the mountains of Chile suddenly finding more space rocks in a few months than entire survey programs used to find in years? Stick around, because the real story here isn't a countdown to disaster. It's something almost the opposite. It's the story of how humanity built a machine specifically designed to find the dangers we couldn't see before. And what it found in its very first test run is starting to change the entire field of planetary defense. To understand why 33 asteroids matters, you have to understand what just got switched on above the Atacama Desert. The Vera C Rubin Observatory sits at roughly 8,900 feet, on a peak chosen because the air there is dry, still, and dark almost every night of the year. It's named after Vera Rubin, the astronomer whose work on galaxy rotation provided some of the strongest early evidence for dark matter, decades before most of her colleagues took the idea seriously. It's a fitting namesake for an instrument built to look at things nobody else has noticed yet. At the heart of the observatory is the LSST camera, the largest digital camera ever constructed, paired with an 8.4-meter mirror and a wide field of view that lets it photograph an enormous patch of sky in a single exposure. Most telescopes are built to stare. Rubin is built to scan. Over and over, night after night, it photographs the same regions of sky, comparing each new image against the last, hunting for anything that moved, flickered, or appeared where nothing was before. That difference matters more than it sounds. A normal telescope might point at one object for hours to study it in detail. Rubin is designed to repeatedly photograph the entire visible southern sky, building what's essentially a time-lapse movie of the universe. Run that process for 10 years, and you get the legacy survey of space and time, the project's main mission. The goal is staggering in scope, mapping billions of galaxies to study dark energy, watching for exploding stars, charting the structure of the Milky Way, and cataloguing the small, fast-moving objects of our own solar system along the way. But Rubin hadn't even started that 10-year survey when this happened. These discoveries came from something much smaller, early test runs that engineers used to calibrate a telescope before flipping it into full operational mode. Think of it as the test drive before the car officially rolls off the lot. And during that test drive, astronomers using Rubin's preliminary data found over 11,000 new asteroids. The discoveries were confirmed independently by the International Astronomical Union's Minor Planet Center, the official global clearinghouse for verifying new objects in the solar system. It became the largest single batch of asteroid discoveries submitted in the past year, and Rubin hadn't even officially started its real job yet. Mario Juric, the astronomer leading Rubin's solar system science, put it simply. He said this first batch of discoveries is just the tip of the iceberg, and that work that used to take years or decades to discover, Rubin will unearth in months. That's the headline most outlets ran with. 11,000 new asteroids. But buried inside that number was something far more specific and far more relevant to anyone wondering whether Earth is in danger. Out of those 11,000 plus objects, 33 were classified as previously unknown near-Earth objects, small asteroids and comets, whose orbits bring them within roughly 1.3 times the distance between Earth and the Sun. Here's where we need to slow down and get precise, because this is exactly the point where headlines tend to run wild. Discovering a near-Earth object is not the same thing as discovering a threat. It's not even close. A near-Earth object is simply an asteroid or comet whose orbit happens to pass through our general cosmic neighborhood, the region of space inside roughly 1.3 astronomical units from the Sun. Earth orbits at 1 astronomical unit. Mars orbits a bit further out. A near-Earth classification just means the object's path crosses into that zone at some point in its journey around the Sun. It says nothing about whether that object will ever come close to Earth itself, let alone collide with it. Scientists at the Rubin Observatory were explicit about this. None of the newly discovered NEOs poses a threat to Earth, and the biggest ones are about 500 meters wide. So why does this batch of 33 matter at all if none of them are dangerous? Because of what it represents about the system that found them. Think about how an asteroid actually gets discovered. A telescope photographs a patch of sky. A moving point of light shows up in successive images, drifting against the fixed background of stars. Astronomers calculate its position over multiple nights, then feed those positions into orbital mechanics models that calculate a preliminary path around the Sun. That orbit gets submitted to the Minor Planet Center, where other observatories around the world can confirm the sighting with their own observations. Only after enough confirmed observations accumulate does an object get a permanent designation and a well-defined orbit. That process, going from a flicker of light to a confirmed, catalogued orbit, used to take astronomers years of patient manual work. Rubin's wide field of view and rapid-fire imaging cadence compress that timeline dramatically. It's the same fundamental science. It's just happening at a pace nobody had access to before. So these 33 asteroids attracted attention, not because they're dangerous, but because they're proof of concept. They're a demonstration, in real data, that Rubin can do exactly what its designers promised: find near-Earth objects faster, in greater numbers, and with better characterization than any previous survey. And remember, this happened during commissioning, before the real survey even started. So if discovering a near-Earth object doesn't mean danger, how do scientists actually figure out which asteroids deserve real concern? It starts with classification. Near-Earth objects, or NEOs, are the broad category we just covered. Anything whose orbit brings it within 1.3 astronomical units of the Sun. Within that population sits a smaller, more specific group called potentially hazardous asteroids, or PHAs. To earn that designation, an asteroid needs to meet two conditions. First, its orbit has to bring it within about 0.05 astronomical units of Earth's own orbital path, which works out to roughly 4.6 million miles, close in cosmic terms, even if it sounds enormous in everyday ones. Second, the object has to be large enough, generally estimated at around 140 meters or more in diameter, that an impact could cause significant regional damage. Meeting both conditions doesn't mean an asteroid is going to hit us. It means its orbit and size put it in the category worth watching closely. From there, astronomers move into orbit refinement. Every new observation of an asteroid, whether from Rubin, another ground telescope, or a space-based instrument, adds another data point to its known trajectory. The first calculated orbit after a handful of observations is always uncertain, sometimes wildly so. As more observations accumulate over days, weeks, and months, that uncertainty shrinks. Picture a thick, blurry tube representing all the places the asteroid could possibly be in the future. Every new observation narrows that tube. Eventually, for most objects, the tube narrows enough that Earth falls completely outside the realm of possibility, and the asteroid gets cleared. That refinement process feeds into impact probability calculations, handled primarily by two systems: NASA's Sentry system, run out of the Jet Propulsion Laboratory's Center for Near-Earth Object Studies, and ESA's independent system called AEGIS. Both continuously scan the catalogue of known asteroids, running orbital simulations to flag any object with even a statistically non-zero chance of impacting Earth in the coming decades. Most flagged objects get cleared within days or weeks as more observations come in. It's a system built on patience and constant refinement, not snap judgments. This is also why international tracking networks matter so much. The Minor Planet Center coordinates observations submitted from observatories across the globe, so a discovery made in Chile can be confirmed by a telescope in Hawaii, then refined further by one in the Canary Islands. No single observatory, however good, sees the entire sky at once. The system only works because it's global. All of this coordination has an institutional home. NASA's Planetary Defense Coordination Office, established in 2016 to oversee detection, tracking, and response efforts for hazardous near-Earth objects. The PDCO doesn't operate in isolation. It draws data from a network of ground-based observatories that have been hunting asteroids for years, including the Catalina Sky Survey in Arizona and the Pan-STARRS telescopes in Hawaii, both of which have spent decades quietly building the catalogue of known near-Earth objects that Rubin now adds to. These surveys work around the clock, scanning the sky on a rotating basis to cover as much of it as possible, as often as possible. On the space side, NASA is building NEO Surveyor, the agency's first space telescope designed specifically for planetary defense. Ground telescopes are powerful, but they're limited by weather, by daylight, and by the simple fact that some asteroids approach from the direction of the sun, where ground observers can never see them coming. NEO Surveyor is built to seek out some of the hardest to find near-Earth objects, including dark asteroids and comets that don't reflect much sunlight at all, by observing in infrared wavelengths from a vantage point in space where the sun's glare isn't a problem. None of this happens in a vacuum either. NASA coordinates closely with the European Space Agency and with international partners through the International Asteroid Warning Network, a coalition of observatories and agencies around the world that share data and would work together if a genuine threat were ever identified. Planetary defense, by design, isn't a one-country project. An asteroid doesn't check borders before it potentially gets close to a planet. For decades, all of this detection and tracking infrastructure existed for one nagging, unanswered question. If astronomers ever did find an asteroid on a collision course, could humanity actually do anything about it? In 2022, NASA finally tested an answer. The mission was called DART, the Double Asteroid Redirection Test, and its target was a binary asteroid system roughly 7 million miles from Earth. A larger asteroid named Didymos, orbited by a smaller moonlet called Dimorphos, about 530 feet across. On September 26, 2022, the DART spacecraft slammed directly into Dimorphos at roughly 14,000 miles per hour. The mission's entire purpose was to find out whether a kinetic impactor, essentially a high-speed battering ram, could meaningfully change an asteroid's orbit. Before impact, Dimorphos circled Didymos once every 11 hours and 55 minutes. NASA's investigation team needed to detect a shift of at least 73 seconds to call the mission a success. What they measured instead was a change of 32 minutes, shortening the orbit to 11 hours and 23 minutes, with a margin of uncertainty of roughly plus or minus 2 minutes. That's not a narrow win. That's a result over 20 times larger than the threshold for success. Why was the effect so dramatic? Follow-up studies suggested Dimorphos isn't a single solid rock, but more like a loosely packed rubble pile, similar in structure to the asteroid Bennu. When DART struck, the impact didn't just transfer momentum directly. It also blasted debris off the asteroid's surface, and that ejected material carried away additional momentum of its own, amplifying the push far beyond what the spacecraft's mass alone could have produced. Later research even found that the asteroid's shape itself changed, and that Dimorphos now orbits roughly 120 feet closer to Didymos than it did before impact. The implications reached further than just the Didymos system. Researchers discovered that the impact's effects rippled outward, shifting the orbit of both asteroids around the Sun, not just the moonlet's path around its companion. Didymos was never any danger to Earth, and there was no way the mission could have put it on a collision course. But the discovery confirmed something planetary defense scientists needed to know. A kinetic impactor really can be an effective technique for deflecting a near-Earth object, with effects that go beyond the immediate point of impact. DART marked humanity's first deliberate attempt to alter the path of a celestial body, and it worked by a wide margin. So DART proved kinetic impact works. But is that the only tool in humanity's planetary defense kit? It's the most thoroughly tested option, but not the only one under serious consideration. A kinetic impactor like DART works by direct, brute force transfer of momentum, sending a spacecraft to crash into an asteroid hard enough to nudge its orbit just slightly off course. Slight is the operative word. You don't need to obliterate an asteroid. You just need to change its arrival time at a given point in space by enough that Earth isn't there anymore when it shows up. Do that decades in advance, and even a tiny nudge compounds into a massive course correction by the time the asteroid would have reached Earth. A second approach, never yet tested on a real asteroid but well studied theoretically, is the gravity tractor. Instead of crashing into the object, a spacecraft would fly alongside it for an extended period, using nothing but its own gravitational pull to very gradually tug the asteroid's path in a new direction. It's slow, it's gentle, and it requires a lot of lead time, but it offers something kinetic impact doesn't: precise, controllable, predictable deflection, useful especially for asteroids whose internal structure is uncertain, where a violent impact might produce unpredictable results. There's also been research into nuclear deflection for the largest or most structurally unpredictable threats, detonating a device near, not on, an asteroid's surface to vaporize material and push the object off course through the resulting force. It remains largely theoretical for planetary defense purposes and carries its own set of technical and political complications. But here's the part that matters more than any of these technologies. Every single deflection method on this list requires time, years, ideally decades, of advance warning. None of them work as an emergency last-minute save. A kinetic impactor needs to be built, launched, and given time to travel to its target, then more time for the resulting orbital shift to add up to a meaningful course change. A gravity tractor needs even more lead time than that, which means the single most important piece of planetary defense technology isn't a spacecraft at all. It's detection. Early, thorough, continuous detection. You cannot deflect a threat you haven't found yet, and you cannot find a threat fast enough if your search tools are too slow, too narrow, or too limited in what they can see. That's exactly the gap Rubin was built to close. 11,000 new asteroids during a test phase is an extraordinary number on its own, but it's nowhere close to Rubin's actual ceiling. Once Rubin's full 10-year survey gets underway, scientists project the observatory could ultimately discover up to 500,000 solar system objects every year. Specifically for near-Earth objects, scientists project Rubin could eventually find nearly 90,000 new NEOs, and some of those are expected to be potentially hazardous. The survey could also nearly double the number of known near-Earth objects larger than 140 meters, pushing the catalogue to roughly 70% complete for that size range, a benchmark that Congress directed NASA to pursue for exactly this reason. Objects above 140 meters carry enough potential energy to cause serious regional devastation. What makes that scale of discovery possible isn't just a bigger mirror or a more sensitive camera, although both of those help enormously. It's the shift toward automated, repeat imaging surveys paired with machine learning systems that can sift through an overwhelming volume of data and flag moving objects far faster than any team of human astronomers ever could manually. Where older surveys relied heavily on astronomers individually examining images for anything unusual, Rubin's pipeline is built to compare millions of data points automatically, flagging candidates for human verification rather than requiring humans to spot them first. Rubin even uncovered the fastest spinning large asteroid ever recorded during this same commissioning period, a discovery that simply wasn't possible with the observational cadence older instruments offered. That's the deeper significance behind the number 33. It's not the size of the discovery that matters, it's the speed, and what that speed implies for everything still waiting to be found. So let's go back to where we started. What if astronomers suddenly discovered dozens of new asteroids moving through Earth's neighborhood? It already happened. 33 of them, found in a matter of months, during nothing more than a test run. And not one of them poses any danger to this planet. That's not a story about a close call. It's a story about a warning system finally catching up to the scale of the job in front of it. For most of history, we found asteroids the slow way, one observation at a time, one confirmation at a time, racing against orbits we could barely calculate with the tools available. Rubin compresses that timeline into something closer to real time. And NASA's planetary defense apparatus, the tracking networks, the impact probability models, the DART mission's proof that we can actually do something about a genuine threat, all of it was built for exactly this moment. A moment when our ability to see is finally starting to outpace the universe's ability to surprise us. Finding more asteroids isn't the danger. It's the opposite of the danger. Every new object catalogued, every orbit refined, every threat ruled out is a problem solved before it ever had the chance to become one. The truly dangerous scenario was always the other one. A large object approaching Earth that nobody saw coming, because nobody was looking closely enough, or fast enough, or far enough into the dark. We're not there anymore. Somewhere above the Atacama Desert, a camera the size of a small car is still scanning the sky tonight, patiently turning the unknown into the known, one photograph at a time. And for the first time in human history, we're not just watching the sky. We're finally starting to see all of it.